Have you read this chapter?
No, sir. Actually, I've been busy with these record work. Now they're trying to make us finish all that.
Okay. But simultaneously, if you read the textbook, no, then if any doubt is there, I can clarify easily. Then you will get easily. You can understand, that is the main thing.
Yes, sir. I'll read it. Yes.
Okay. So nomenclature over yesterday. Isomerism. This isomerism means same molecular formula and a different structure. Those are called isomers. It will come in the class 11th also in organic chemistry. Do you have any idea about isomerism?
Yes, sir. Like same molecule
Example,
form and
CH3O,
structure.
CH3. It is the ether in the organic chemistry. CH3, CH2OH. It is the ether. It is the alcohol. So both molecular formula is same. Two carbons, 6 hydrogen, one oxygen. Same molecular formula, but different structure, different chemical and physical properties. These two are called isomers. This phenomena is known as isomerism. Similarly, in inorganic, here also isomerism is there. That isomerism mainly two types: stereoisomerism and structural isomerism. In the stereoisomerism, again two types: geometrical isomerism and optical isomerism. Geometrical isomerism and optical isomerism, here connectivity almost the same. There is no change. There is no change in the structure. Three-dimensional arrangement is different. 3D arrangement is different. The connectivity almost the same. 3D arrangement is same. Example, in organic chemistry, I can explain easily. So here, A, B, C, D. Here, A, B, D, and C. These both are same or different?
So it has like the different structure.
See, structure is same now.
No, it's same structure. Yes,
Same
same. It's
structure, but
mirrored.
mirror images. 3D arrangement
Yes.
is different. Here right side D is there, here left side D is there. But the D is connected with middle carbon. Of course, middle carbon connected same. Okay, but 3D arrangement is different. Connectivity is same. Okay, this type of structures. So this is the example for optical isomerism. This is the example for optical isomerism. And geometrical isomerism, hydrogen CH3, hydrogen and hydrogen, CH3 and CH3. Do you know this is called cis? This is a trans. Here, see, if I give the numbering, IUPAC numbering 1, 2, 3, 4. Here 1, 2, 3, 4. See, on second carbon, hydrogen is there. Second carbon attached to hydrogen, methyl. Second carbon attached to hydrogen, methyl. Second carbon connected with double bond. Second carbon connected with double bond. Third one, hydrogen, methyl, hydrogen, methyl. Okay, the connectivity almost same. There is no change, isn't it?
Yes, sir.
But the thing is here, methyl and methyl both are same side. Here methyl and another methyl is opposite side. Okay, this type of isomerism is called geometrical isomerism. Geometrical isomerism. Okay, so geometrical and optical and structural. Which one is a structural? Structural, I given you this one. This ether and alcohol. Here structure is different. See, the connectivity completely different. Here CH3, between oxygen is there. Here oxygen, one side carbons are there, one side only hydrogen is there. Connectivity completely different. This type of structures are called structural isomerism. The connectivity is different. Are you getting?
Yes, sir.
Right. Now, in the structural isomerism, you can see linkage isomerism. Linkage means link is different. The connectivity is different. Then coordination isomerism and ionization isomerism, solvate isomerism, one by one we'll discuss. Now, first heading, geometrical isomerism. See, cis-trans, that is organic. I give an example. Now, cis and trans, same groups, adjacent is there, that is called cis. Same groups on adjacent carbon, on adjacent positions, that is cis. Same groups on opposite position is there, trans. Geometrical isomerism. Understood this?
Yes, sir.
Okay. So this much only, geometrical isomerism. Next. Suppose here, this is the NH3. Suppose instead of this chlorine, here it is NH3 is there. Is it exhibit geometrical isomerism or not? Is it called cis?
Yeah, because of NH3.
But cis means at least minimum 2 different groups should be present. See, actually, the geometrical isomerism, is it exhibit or not, will be decided by changing 2 groups. See, now this is the given molecule. Okay, now what I'm doing, I am exchanging any 2 groups. Which 2 groups? Suppose these 2. These 2 groups I'm exchanging. These 2 groups I'm exchanging here and there. Now, NH3, middle platinum is there. Here chlorine and here NH3. Now these 2 structures are same or different. So how we will get to know? Just you take this molecule, keep it on this and rotate it. See, now looking like a mirror images, isn't it? NH3. Top NH3, niche, down chlorine. Top NH3, down chlorine. It is looking like mirror images. Yes?
Yes, sir.
So now, is it these both are same or different? This question is raised. Then what you will do? This molecule, put on this molecule, original molecule. This image, put on this, then rotate it. So same, it will align or not?
It will not align.
If you keep it as it is, not aligned, but if you rotate 90 degrees.
Oh yeah, then yes, sir. Yes, it will align.
This chlorine will come here, this NH3 will go there, then this rotate. No?
Yes.
Then as it is. That means these both are same.
Yes, sir.
These both are same. It's not different. Okay, so in this case, there is no geometrical isomerism. So now you understood geometrical isomerism when it will exhibit. Whenever if we exchange the molecule, if it gives a new molecule, then only geometrical isomerism is possible. Here it is not generating any new molecule. Here 3, if 3 NH3 are there, by exchanging 2 groups, there is no new molecule generating. That's why not exhibiting geometrical isomerism. Then when it will be exhibit, so in this case, two different groups. Then in this case, geometrical isomerism is exhibit. Understood?
Yes, sir.
So M, A, B, C, D, all different is there. Yes, geometrical isomerism possible. Then M, A, B is there. Then also geometrical isomerism possible. Then M, A, B3 is there. No geometrical isomerism. M, A4 is there. No geometrical isomerism.
So geometrical isomerism basically means that the mirror image should be non-imposable, right, on top of it?
Yes. It is completely diastereomers. See, trans and cis, even mirror image is not possible.
Yes, sir.
There is no mirror images. You can see anyone. First of all, there is no mirror images in the geometrical isomerism. Okay.
Yes, sir.
Here, all four different is there. Okay, fine. At least two different groups are there. 2 and 2. It's okay, fine. But 3 are same. 1 is different. Also, there is no use. All 4 same. There is no geometrical isomerism. These are the conditions. Done.
Yes, sir.
Next, if 4 groups are there like that, if 6 groups are there, M, A, B, C, D, E, F, all 6 different is there. Okay, then also geometrical isomerism is possible. So at least see 2 groups should be different. One is chlorine and ammonia is there. It's okay, but the chlorine should be 2. Then geometrical isomerism is possible. Only 1 chlorine is there, remaining all ammonia, then not possible. So I'm writing here not possible. Ma6 is not possible. Ma5B also not possible. Remaining possible. Understood?
Yes, sir.
Ma6 means all same ligands are there. Then also there is no cis and trans, because all same means how can we say which is opposite and same side? And only one is different is there. Then also we cannot decide.
And also geometrical isomers form only when like we can form cis and trans compounds.
Yes.
Okay, sir.
Right. Okay. Here also cis adjacent is there. Cis opposite direction trans.
Yes, sir.
Next, here also cis and trans is there. So what is this En? En means ethylene diamine. Ethylene diamine is a bidentate ligand. Yesterday we discussed ethylene diamine, CH2, CH2, NH2. Only one ligand. It can form one bond. It can form one bond, 2 bonds. It is forming a ring. Right. Now, in this geometrical, 2 more. Cis trans already we discussed. One facial and meridional. 2 words are there. Facial and meridional. When this one, whenever 3 ligands, see M, A3, B3. A3, B3 equal percentage. A3, B3 is there. Then facial and meridional, we are telling, not cis and trans. If only 2 are there, cis and trans. If 3 are there, we are using facial and meridional name. You can see the spelling, facial and meridional. Okay, what is this? Facial means in that name only the face. It is forming one face. One triangle face is forming. One triangle face is forming. Facial. Meridional meridional is, see, first you need to understand this. This is the octahedral shape it is. I've understood this shape. One square is there. One square is there. All four corners, four groups are there. Above the group, above the square and below the square groups are there. NH3 and NH3. This is called actually octahedral geometry. Short form. Have you imagined this structure, octahedral shape?
Yes.
It is actually diamond shape also, we can say. See, it is like this. One square. Now the square is visible now clearly.
Yes, sir.
The square, top of the square, one NH3 is there. I am connecting from all corners. Okay. Here one triangle is forming. One triangle, second triangle, third and fourth. Four triangles are forming above the square. Yes?
Yes, sir.
Square is there. From this NO2, NO2 corners and the top one triangle. This is the one triangle is forming. And right side also one triangle, left side also one triangle, back side also one triangle. Total how many triangles? 4 triangles are forming. Yes?
Yes, sir.
Same below also 4 triangles will be forming.
Yes, sir.
So this is total how many? Octa, 8. 8
Eight.
triangles are forming. Octahedral. Actually, this is in the mathematical word, that is hydral form. Octahedral. 8 hydrons are there. Okay. Now, okay. Because of these 3, if it is forming any one triangle shape, that is called facial. And these 3 same groups, three same groups, NH3, not NH3. I will remove this. Now you can see this NO2 group, this NO2 and NO2. This one is on the plane. Okay. On the plane, this plane is bisecting the octahedral shape. This plane is bisecting. Actually, this is the structure, whole structure. In this structure, here half of cutting this plane. Okay. What is this one? This one is forming one triangle. You may think, sir, here also one triangle is there. It's a triangle, okay, but it is the outside surface. Face is forming here. It is not face. See, in the this one square, in the square, diagonal and this one. So this total octahedral is bisecting by these 3 groups. You have to little bit imagination. Understanding
Yes,
or not?
sir. Yes, sir.
Okay. So these 2 difference. This is the outside. Face is forming. Here it is bisecting. That's why meridional, it is a facial. You can search in the Google 3D pictures, you will get it easily, you can understand.
Meridional I understood, but facial little like.
Facial not understood, facial only easy. See, it is a square, right?
Yes, sir.
Here A, B, A, it is there like this. B. This one is B. Here in the middle, maybe cobalt or platinum, something in there. This B and B. Here, this triangle is forming. BB, and this one is a BB. This triangle, it is a facial. On the square, two edges, then top of the square or bottom of the square. Any one face. See, you understood the 8 faces now.
Yes, sir.
Out of the 8 faces, any one face. If it is forming, that is facial.
Okay, so facial is like if it is from the square two edges to the top one.
Yes, either top
like,
or bottom.
And meridional is like within the square.
Yes.
Okay, so yes, sir.
Okay. Then optical isomerism. You can see optical isomerism, the connectivity is same, but these are the mirror images and not superimposable also. Same in the organic chemistry, same definition here also. Properties almost same. Here 3D, you need to understand. These are the mirror images. If you put it on this, those are not superimposable. But actually the structure is not like this. The structure is, you have to it is a square cobalt ethylene diamine, right? NH2. It is one ethylene diamine. One top is there, one bottom is there, right? NH2, NH2. Then NH2. This is the actually structure. It is given like this, but actual structure is like this. Okay, understood structure? These are the CH2 or CH2s. Ethylene diamine. Okay, understood?
Yes, sir.
Now, mirror image. The mirror image I'm drawing very small. The mirror image is like this. These two are there. Then square will be there. Okay. Bottom is like this, and here it is like this. Back side of. It's not exactly I'm drawing, but so like this is there. See what I am drawing this lines, that is a square actually. Okay, so if you put it on this, first of all, these are the mirror images. See here, left side, one square type is there, this one. If you put it on this here, not matching. If you rotate also, it won't be matched. If you rotate 360 degrees also, it never match. Maybe thinking that, sir, if I rotate 180 degrees, so exactly it will come this side. Okay, fine, it will come. These two will be matched, but it will goes upside, it will go downside. Okay, so in the virginal molecule, this is the bottom side is there, but it will come top side. If you rotate 180 degrees, this part will be matching. This one and this one will match, but these two cannot match.
Yes, sir. Yes.
This is a structure actually. This is the structure. These two are. Is it visible now?
Yes, sir.
Same ethylene diamond example. Now you can see the thick line means towards us, means outside the plane. Dotted line means away from us, backside. Normal line means on the paper, on the desktop. Dotted line inside the desktop, thick line outside the desktop. Okay, this is the imagination. You can see the mirror images are there. Now you take this one and keep it on the first one, rotate it 360 degrees. Either it is aligned or not, tell me. If you take it as it is it possible? See, I am taking as it is. See here, right side CH2 CH2 is there, here left side is there. That means as it is, though not possible. Yes?
Yes, sir, not possible.
Not possible. Then what to do? Rotating. How much degrees I'm rotating? Whatever you rotate, it's not possible, but still, if you try, suppose.
It won't be possible because, like, yeah, it won't be possible.
That's only. It should not be possible. Then only those are optical isomerism. Mirror images and non-superimposable. These are the optical isomers. Okay, understood the structure?
Yes, sir.
In the NCERT, what is given like this is given. They think that's if you rotate 360 or some certain degrees, so it will be aligned. This picture will be aligned, but actually the picture is not like this. That's why I showed that one. Okay, understood?
Yes, sir.
Okay, here dextro and levo. How we will get to know? No one knows. One thing you have to give dextro, other one is levo. That's enough. One is dextro means other one is levo. Because mirror images quite opposite rotation is there. One is L rotation, one is D rotation. Dextro means D, levo L. That's enough. Next. Here, cis-trans we can give. 2 are there, same side and opposite side. Cis-trans we can give. Then dextro and levo. Then dextro and levo, how can we give the dextro and levo optical isomerism? For optical isomerism, only one property is required here, mirror image, and should not be superimposable. Okay, if that property is following, those are exhibiting optical isomerism.
Yes, sir.
Optical isomers here. These two are not mirror images, but it can exhibit one more mirror images individually and a non-superimposable. Then that is optical isomerism, exhibiting optical isomerism. And here plane of symmetry. Levo rotating. Here plane of symmetry is there. In coordination entity, the type of cis isomer. Only cis isomer show optical activity. The trans one, it is a trans, no optical activity. No optical activity. Why? Because here plane of symmetry is there. If plane of symmetry is there, there is no optical activity. Do you know that? Don't know.
Sir. No.
Optical isomerism. See, what is the condition for optical isomerism? Mirror image and non-superimposable. Then those are exhibiting optical isomerism. And in any molecule, if plane of symmetry is there, plane of symmetry and center of symmetry is there. If these two are any one of these present, then no optical activity. No optical activity. Okay. Now, what is the plane of symmetry? Plane of symmetry means if any one plane, if it bisect exactly half of, means identical parts, exactly identical parts, that is called plane of symmetry is present. Any one imaginary plane, if it bisect as identical parts, that is called plane of symmetry is present. Understood?
Yes, sir.
Now here, if I take the one plane here, imaginary plane, so right side ethylene diamine, left side ethylene diamine, the chlorine and chlorine getting half of, exactly, breaking half of. So right side part and left side part is exactly mirror images. So indirectly I can define this one, plane of symmetry. Within the molecule, listen carefully, within the molecule, if plane of symmetry is there, that is only, within the molecule, if mirror image is there within the molecule, that is only plane of symmetry. Understood?
That is like if we take the mirror image of this molecule, it should be the same.
Yes.
Okay. That
Okay.
is plane. That is of that. Then only it is plane of symmetry.
Actually, plane of this definition I given that within the molecule mirror image. Actually, according to textbook definition is one imaginary plane. Any one imaginary plane, if it bisect a molecule into two identical parts, then that is called plane of symmetry present.
Okay.
One imaginary line. I'm taking this imaginary line. It is bisecting the molecule into two parts, two identical parts. Two parts the common, but identical parts. Right side, how it is there? Exactly left side. Example, see A is there. Here, if I cut it like this, right side and left side exactly same. So plane of symmetry is present. Okay. B is there. Letter. Okay. If I cut it like this, mirror image type is there. Exactly. Above and below the same is there. Plane of symmetry is there. Okay. If I take S, plane of symmetry is there.
No, sir.
On this one or on this one, there is no plane of symmetry. So plane of symmetry means that. Understood?
Yes, sir.
Right. So what is the conclusion here? In any molecule, if plane of symmetry is there, there is no optically active. That is the thing. So here cis and trans, two isomers are exhibiting, and here this is a cis and this is a trans. In the trans, plane of symmetry is there, so optically inactive. The cis exhibit as optically active. In the optically active, dextro and levo, it will be there. Draw the structure geometrical isomerism of this one. So the question will be like this: draw the structure of geometrical isomerism. Here 2 NH3 2 is given. One is geometrical isomerism means cis trans type we need to draw. One is NH3 adjacent, one is opposite. Adjacent and opposite. Cis and trans. Done. Then out of the following two coordination entities, which is chiral or optically active? Just now we discussed cis and trans is there. So in case of cis, in case of trans, plane of symmetry is there. So optically inactive. Two entities are represented as. Out of the two, A, cis is chiral, optically active. This is the optically active. Here there is no plane of symmetry, you can check it. You may think that, sir, if I cut it like this, but this structure is actually, it is the square. Right, this is a square. This is the above and one of the corner and below. Okay, if you cut it any angle, any direction, is it possible to bisect exactly identical parts?
We do it like as a horizontal line.
Horizontal line, okay. So if you do horizontal line, this chlorine and chlorine, it's okay, fine. But here it is the top is there and the bottom is there. Horizontal line means here, this one only, na, you are telling like this?
Yes, sir, yes.
So here, this one and this one, okay. So from here to this corner, here bottom one is there. Okay, here this ligand is there. Then here ligand is there. Okay. Where it is, see, horizontal line means here it is, this vertical line also will be cut. This one and this one also it will be cutting. Okay. And this one is remain. This one remain upside. This one remain downside. This one remain upside. This one remain downside. So it's not mirror image.
But
see,
which way are we
this one,
taking?
okay, this one only, na? Both are same, I think. Yes, two chlorines, right? Okay, this one only, but here two chlorines are there remaining as it is. This right side is two chlorines we can cut it, no problem. Tell me here, if two chlorines are there, one chlorine that side, one chlorine inside the plane, and one chlorine is outside the plane, it's okay. If you are bisecting top to bottom, that means this NH2 will bisect, this NH2 will bisect, right?
Yes, sir.
And this NH2 is inside, this NH2 is outside. That much clear. Yes?
Yes, sir.
But this CH2 is the top side. This CH2 is the bottom side. How it is identical? It's not identical. Identical means here it should be like a mirror image. Again, within the molecule mirror image. Within the molecule mirror image is there. Then plane of symmetry present.
Okay, sir.
Okay.
Yes,
If
sir.
that imaginary line, this chlorine, okay. But here above part is there. This is actually one square. Below the square is there and above the square is there. How it is same? It's not possible.
Okay, yes, sir. Like the chlorine is like on the same plane, but then the other part is one is top, one is bottom. So
Ha,
we can.
ha,
Okay,
that is
yes,
it.
sir.
Okay.
Okay.
So here is Z. The chlorine exactly cutting half of right side and left side is there. So okay, mirror images type is there. That is only planar symmetry. So optically inactive. This is optically active.
So over here, chlorine is like top, bottom, and then the remaining part is on the same plane.
In the first one?
The second one.
Ha, yes, yes.
Okay.
Now geometrical isomerism and optical isomerism over. Then linkage isomerism. So in the linkage isomerism, in the word only is there link. So some ligands are like this. Within the ligand, two donors are present. That ligands are called ambidentate ligands. Ambidentate ligands. Two donors. That means NCS is there. Here, sulfur also can form the bond, and nitrogen also can form the bond. Example, well-known compounds in the organic chemistry, RCN, cyanide, and RNC, isocyanide. Have you seen these type? RNO2, nitro compounds, RONO. Okay. So here NO2 group, okay. Sometimes nitrogen also can connect and oxygen also can connect. This type of groups are called ambidentate ligands. Okay.
Yes, sir.
So here in case of NCS is there. So MNCS also can form, MSCN also can form. Here sulfur is forming the bond, here nitrogen is forming the bond. So this type of linkages, differences are there. Those are called linkage isomers. Sometimes ONO is forming, in one molecule is ONO is forming, in another molecule NO2 is forming. Molecular formula is same, but what is the different? The linkage is different. The ligand link with metal is different. Different atoms are donating. So this type of isomers are called linkage isomers. Okay.
Yes, sir.
So example here is given, NH3 taken 5, NO2 is there. So which type of link isomerism is possible means NO2 is there means, yeah, linkage isomerism is possible.
Yes, sir.
Next, coordination isomerism. In the coordination isomerism, coordinations, two coordinations are there. CO NH3 taken 6 and chromium CN6. The coordination means coordination, two coordinations will be there. Then simply this cyanide and NH3 completely shifting, exchanging. Now cobalt is with ammonia molecule, right? In the next coordination isomerism, cobalt with cyanide will come. See, cobalt with cyanide. Okay. So what they did, just simply metal ions they exchange. Either you can exchange the ligands or metal ions, almost same. Okay. Exchange the metal ions. Chromium is coming here, cobalt is going there. Here cobalt and NH3 combination. Here chromium and NH3 combination. Okay. In the coordination isomerism, two coordinate complexes are there. Their metal ions are exchanging. That type of isomers are called coordination isomers. Is it clear?
Yes, sir.
Then ionization isomerism. Ionization isomerism means ions forming different. See, this molecule is there and this molecule is there. CONH35, CONH35, bromine SO4, bromine SO4. Both are same molecular formula, but it is donating Br minus, it is donating SO4 minus, SO4 minus 2. Ions in the water, these are giving different ions, this is giving different ions. Molecular formula is same. So this type of isomers are called ionization isomers. Understood?
Yes, sir.
So here one more point, and why it is giving Br and sulfate. See, outside the bracket, whatever ions are there, those can ionizable. Those can ionizable. So if you put it this complex in the water, we will get it one complex Br plus inside, then so this complex plus, then Br minus. If you put it in the water, here one complex will give here +2, then sulfate -2. That means bracket outside, whatever are there, those can get separate. Within the bracket, whatever are there, those will be in the bracket only. In the bracket, cobalt is there, or bromine is there, which one is there, we don't know. If you do in this molecule, if you do the bromine test is negative. It won't give bromine test. Sir, bromine is there, but within the bracket is there. So that bromine cannot give the test. Okay, that's why these are called complex compounds. Those molecules are there, but those are not giving test. Are you getting?
Yes, sir.
Okay, final conclusion is outside the bracket, whatever are there, those will get ionization. Within the bracket, those are not giving any test. Those are not ionizing, first of all. That's why it is giving bromine, it is giving sulfate. So two different ions are giving, that's why these are called ionization isomers. Next, last one, solvate isomerism. Solvate means generally solvent. So here water molecule difference is there. Water molecule. See, chromium H2O6 Cl3. Here chromium H2O5 Cl. Outside 3 chlorines were there initially. 1 chlorine came inside and 1 water molecule coming outside. That's only the water molecule variation. This form of isomerism is known as hydrated isomerism also. Why? Because hydrated means water molecule. Hydrate, water molecule difference is there. Hydrate isomerism. In case where water is involved as a solvent, this is similar to ionization isomerism. Solvent isomers differ by whether or not a solvent molecule is directly bonded to the metal ion or merely present as free solvent molecules in the crystal lattice. This story is there, but final conclusion is just you need to write one example. Water molecule variation. Here 6 water molecules are there, here 5 water molecules. Outside no water molecule, here 1 water molecule is there. Okay?
Yes, sir.
Bonding in coordination compounds. Yeah. The starting. This one. See here, bracket is there. Outside 3 chlorines are there. Okay, actually this molecule is CONH3 6 times Cl3. It would be like this. Okay, that means these are giving 3 chlorines. That is only showing here 3 chlorines, chloride ions giving. So which type of salt means here sometimes they will ask you 1:3 electrolyte. This is called 1:3 electrolyte. What is this 1:3 electrolyte? 1 is cation and 3 anion. Means one is bracket, one is complex and 3 ions. 1:3. What is electrolyte? Electrolyte means which can pass the electricity. That is electrolyte. 1:3 electrolyte. It is 1:2 electrolyte, 1:1 electrolyte, 1:1 electrolyte. You understood this table? 1:1 electrolyte means what? Why they are calling 1:1?
Yes, sir.
This bracket is 1 ion and another, the chlorine is 1 ion. 1 and 1, 1:1. Here 1:3, 1:2, 1:1, like this.
So the anion comes first and then the cation.
Cation first generally. Na plus Cl minus. This is the cation, no? This is the cation.
But like 3 plus is given there.
And see, 3Cl minus means minus, anions are 3. That is the meaning. Maybe you are thinking this is the 2, this is the 1. No. The 2Cl minus is the 2. Cl minus ions are 2.
Yes, sir. Okay. Okay, yes, sir.
Okay. It is 3, 1, 2, 1. It's not like that. Cation is 1 and anion is 1. Here, cation is 1, anion 3. 1:3. Okay. Here, see, imaginary line like this. It is one complex. Then here, chloride ions. How many are there chloride? 3. 3. 1:3. It is not oxidation number. How many particles? That is the mean. Just it is one complex and 3 ions. So 1:3.
Yes, sir.
So they will ask the question like this. One molecule is there and it is reacted with AgNO3. Then it is giving 2 moles of AgCl precipitation is giving. 2 moles of AgCl precipitation is giving. So what will be the structure of this first one? Moles of AgCl precipitated is given like this. Then what will be the structure? How to write it? Palladium. See, 2 AgCl is giving means 2 chlorine should be outside. Understood? Bracket. Outside the bracket, 2 chlorine should be present. Then only that it can give this AgCl, 2 moles of AgCl. NH3 taken 4 times. 4 times. So this is the first question answer. Hello.
Yes, sir.
So why I written outside 2? How I get to know 2 chlorines are outside? Here it is given information. AgNO3. Moles of AgCl precipitate means 2 moles of AgCl precipitate per mole of the compound with excess of AgNO3. I am adding AgNO3, it is forming 2 moles of AgCl. That means 2 chlorines are outside, then only giving AgCl. Got it? Suppose the last one. Here, there is no AgCl is forming. That means platinum, 2 chlorines, NH3 taken twice. Outside, there is no chlorine. Nothing. Understood?
Yes, sir.
Okay, this is giving information here. One AgCl forming means 1 chlorine is outside. 1 chlorine outside means 4 ammonia and 2 chlorines are inside. Like that, you need to write. Then here it is asking that what is the coordination number? Coordination number, you can see the first one is coordination number 4. Yesterday already I discussed coordination number means what? Coordination number means nothing but the number of bonds. The palladium is connected with how many ammonium? 4 ammoniums. Coordination number 4. 4 bonds are there. Like this, palladium. NH3 here, NH3 here, NH3 here, NH3 here. All coordinate covalent bonds giving electron lone pair to palladium. Coordination number is what? 4. Understood?
Yes, sir.
Here nickel dichlorine and 6 water molecule. 2 moles HCl means 2 chlorine outside, 6 H2O inside. 6 H2O inside. What is the coordination number? Obviously 6. Next here 4 chlorines, 2 HCl. Total 6 coordination number. Then here 1 chlorine
So
outside. Yes.
we have to. So then in the second one, it will be like 8, right?
8. How 8? See, the structure you need to write. Nickel H2O 6 times, chlorine 2. This is the structure, no? See, 2 chlorines giving, no? That means chlorine is outside, not inside. You are counting 6 water molecule and 2 chlorine. Total 8 are there. Yes?
Yes, sir.
But the 2 chlorines are outside the bracket, no?
Oh, yes, sir. Then what about like for the third one?
Third one is giving 0. 0 means there is no outside. Everything is inside only. 4 chlorines, 2 HCls.
Okay. Yes, sir.
Total 6 only.
Yes, sir.
Okay. So remaining also like that. Valency bond theory. So now till that time what we discussed and how many types we discussed. Isomerism we discussed, nomenclature we discussed, isomerism we discussed. Okay. Now bonding in coordination compounds. We are talking about Ma6 is there, Ma5 and B is there. It's okay. What now in between metal and ligand, what type of bonds are there exactly? Even 2-3 times I explained, sir, that is coordinate bonds. Really, is it coordinate covalent bond only? Okay, that is big question mark. The chapter name itself, coordination compounds, but the bond is not coordinate bond. But initially we thought coordinate bond only. Of course, we learn half of the chapter like that only. Then slowly, different scientists they given. It is similar to atomic structure. In the atomic structure, what we learn initially, Thomson will come and he will say something, and then Bohr will come. Then Rutherford will come. He will say something. Then Bohr will come. So step by step, we will move. Okay, every time he told this much, so many limitations are there. That's why we are going next theorem. And that is also has a limitation. So next, so like that, similar. Here initially we thought coordinate bonds are there. The chapter name is there. It's okay. But actually now we started what type of bonds are there in between metal and ligand. This is the main topic now. So it is explained by so many. So now it is explained by VBT. Valency bond theory. Valency bond theory is one thing. Then CFT, crystal field theory. Then ligand field theory, LFT. And finally, molecular orbital theory, MOT. These many are there. We shall focus our attention on elementary treatment and the application. VBT and CFT only we will discuss here. That means still LFT and MOT out of the syllabus. Okay.
Okay. Yes, sir.
So what is VBT? Valency bond theory. In the name only, the valency electrons bond, the valency electrons and valency orbitals are involving in the bonds. So this hybridization, do you know the hybridization? sp3 dsp to this?
Like this.
sp3 means tetrahedral, dsp. At least sp3 tetrahedral, do you know this? sp means
No.
linear, sp2 trigonal planar, sp3 tetrahedral, sp3d trigonal bipyramidal, then sp3d3, sp3d2 octahedral. This is only just before we discussed above the triangle and above the square and below the square. Do you know this?
So I don't know it like properly, but yeah.
Okay. See, CH4 is there and H2O is there. Do you know the hybridization of CH4? In the CH4 carbon hybridization, do you know? Number of sigma bond plus lone pairs.
Yes, sir.
What is the hybridization of carbon here? Total 4 bonds are there, no?
Yeah, so 4
No.
sp3.
Yeah, sp3. 4 bonds are there, 4 orbitals are involving. That's why 4 orbital. Which orbital? Generally, hybridization will start from s orbital. S means only one electron, one orbital is there. So then remaining are p orbitals. Total 4 orbitals, sp3. In case of H2O here, oxygen has 2 lone pairs. So 2 lone pair plus 2 sigma bond, again 4, then sp3. Okay. So now 4 orbitals. These 4 orbitals are arranging 3-dimensionally like this. You can take 4 balloons and hold it, all 4 mouths together. Then what will automatically the 4 balloons will arrange in the 360 degrees. Those are arranging. So the bond angle will be 109.5 degrees. 109.5 degrees. If you take 4 balloons, so the shape, it will come like this. That shape only here, 2-dimensional, you will mention like this. These 2 are on the plane. It is inside the plane. It is outside the plane. This is called tetrahedral shape. The tetrahedral. This one is the trigonal planar. This one is the linear. Here 5 are there. One triangle and above the triangle and below the triangle. Trigonal bipyramidal. If 6 are there, square, above the square and below the square. So this is simply known as octahedral complex. Okay. Right. These are comes in the class 11th chemical bonding chapter also. Now, extra, other than this, maximum it's okay, but other than this, here sp3d2 and d2sp3, these both are same. geometry. You can see octahedral. And sp3d, it's okay, trigonal bipyramidal. Here one extra is there, dsp2. dsp2, it won't come in the organic chemistry. dsp2, it will come here, dsp2. This is the square planar. This is the square planar. dsp2, it will come. This is only extra. That means here, if 4 ligands are there, means it may be sp3 or dsp2. If it is sp3 is there, tetrahedral geometry, dsp2 is there, square planar. 6 ligands are there, either it may be sp3d2 or d2sp3, both cases octahedral. 5 is there, only one thing, that is trigonal bipyramidal. So mainly confusion only 4, when 4 ligands are there, sp3 dsp2. Okay, this is only little bit confusion, remaining case almost easy. Sir, here also sp3 d2 and d2 sp3 is there. This is also easily we can identify. I will tell that. Now what's happening here? I'm taking one molecule, CONH3 6 3 plus. CONH3 6 3 plus. Tell me cobalt atomic number. 27. Iron
Yes.
cobalt, manganese iron cobalt, manganese 25 rupees kg. Okay, you have to remember atomic numbers. Manganese iron cobalt 4s2 3d7. Right. Here, what is the cobalt oxidation number?
Cobalt oxidation number. For NH3, it will be 0, right?
Yes.
So then it will be +3.
Yes, +3. So cobalt electronic configuration 4s2 3d7. Now tell me cobalt +3. That means 3 electron I need to remove. From where I have to remove 3 electrons? 4s 0 3d 6.
3D.
Student will confuse here. They will remove 3 electron from D only. No. Always you need to remove electron from 4s first.
Okay.
Because it is a valence shell.
Yes, sir.
Right. So this much understood now?
Yes, sir.
Now I am writing again CO +3. CO +3. 4s0 means 3d6 4s0. Isn't it? 3d6 or 5. 27 means right. 3d6. Now 3d6. D means 5 boxes. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 6 electrons. Here 4s is J. 4s is this is the 3d. It is the 4s. Then 4p. Then 4d is there here. It's okay. Leave it. Okay. This much you understood?
Yes, sir.
Cobalt +3 electronic configuration I written. That's enough. Then electron distribution I written. Now this cobalt +3 reacting with NH3. It is accommodating for 6 ammonia molecules. Okay. Now what will happen when NH3 is NH3? It can give a pair of electrons. So when NH3 is trying to give that time, these electrons will get pair up. These electrons will get pair up. See, suppose at our home, 3 BHK, 4 BHK is there, study room and XYZ rooms we will arrange. Whenever guest is there, we will vacant some rooms. We will adjust. Yes.
Yes, sir.
So similarly, when the guest is coming, these are arranging itself. This electron pairing here. Okay. So total 4 are there. So these 2 electrons getting pair up here. So what's happening? 1, 2, 3, 4, 5. So already first one lone pair was there. This paired electrons are there. It's okay, fine. 1, 2. 1, 2, 3, 4. Total 6 electrons. Done. Now ammonia is coming. Guest. This is the ammonia electrons. Ammonia electrons I am showing with cross. This is also NH3, NH3, NH3. How many? 3. Here NH3, NH3, NH3. Okay, this much you understood?
Yes, sir.
NH3 giving a pair of electrons, 2 electrons. It is accommodated in this orbitals. Now this NH3 given electron to whom? Which orbitals? D2. This is the D na completely. D. How many orbitals? D? 2. Then S. Then P3. D2 sp3. This is the hybridization. Understood?
So the unpaired electrons
Yeah, unpaired electron becoming pairing.
become pairs over there.
Yes. This one is going here and this one is coming here.
And then the lone pairs go to the other spaces.
Yeah, lone pair of ammonia is occupying these empty orbitals.
All of them.
All of them.
Okay.
So how many ammonias are there? 6 are there. So 2 are joining with the 3D. Then 1 is joining in S. The remaining 3 are joining in the P.
Okay.
Total,
yes,
these orbitals filled. D2 sp3.
And, the number of lone pairs is dependent on the number of ligands, right?
Yeah.
Yes, sir.
Yes. Okay. So that like this. So here hybridization word, why they mentioned, see, according to this picture, D orbital and S orbital and P orbital actually different. S orbital shape is actually spherical shape. P orbital is dumbbell. This is the double dumbbell shape. Okay. So if NH3 also filling like individually, then this bond will be weaker bond. This may be stronger bond. It may be different bond. So 3 types of bonds it should be. But actually experimentally what happened, these NH3 and this ligand CO and NH3, all 6 bonds are equal. All 6 bonds are exactly identical, strength and length. So what's happening in that? So actually I written like this, but what's happening here? These are undergoing hybridization. These are undergoing hybridization. So there is no gap here. There is no S orbital, there is no P orbital identity. Each one is D2 sp3. Each one is D2 sp3. So I should write like this. I should write like this. So here 1, 2, 3 over pairing. After that 1, 2, 3, 4, 5, 6. Now each one, which orbital it is means it is not D orbital. Now it is D2 sp3. Then last one also D2 sp3. That's why there is no variation in the bond length and bond strength. Understood?
Yes, sir.
So the hybridization word means almost equal energetic orbitals intermixing and forming a new degenerated orbitals. That is called hybridization. You can see here. So cobalt plus 3 given, it's okay, fine. S and D, empty is there. So now 2 d orbitals and s orbital and p orbital. Total 6 orbitals are forming here. This is the hybridization. Once getting hybridization, this NH3 is donating electrons to this. I written with cross, here it is given with this mark, no problem, both are same. Understood?
Yes, sir.
It
So
is
like
inside.
all the orbitals will join together and form a single one.
Yes. Almost equal energetic orbitals. And S and okay, that is hybridization. And one more example, 3D, 4S, 4P, 4D are there. Then here sp3 d3, here this one is not giving electrons, this 3D is not giving any orbitals. Here d is involving from 4D. If two possibilities are there, d from here also, from there also. If d is involving from 3D, that is inner orbital complex. If d is participating from 4D, that is outer orbital complex, because outside is there, outer orbital complex. Outer orbital, it is inner orbital complex. Okay.
Yes, sir.
Now then, next question is, when it is involving outside d orbital and when it is involving inside orbital, this is the big question mark. So there is no proper information in the VBT, but still we have to know that whenever fluorine and halogens are there, halogens, fluorine, chlorine, bromine, iodine is there, outside D is involving. When ammonia, when NH3 and cyanide, cobalt, carbon monoxide, carbonyl, okay, whenever these are there, inside D is involving. Inside D is involving. Why? Because actually later we will get to know these are the strong ligands. These are the strong ligands. When strong ligand is coming, then these electrons are getting pairing. So here vacant orbitals available. The vacant orbitals occupied by this. Generally, I will explain in the classroom. So whenever principal and coordinator is coming, section in charge is coming, immediately the students will sit in the bench properly. Otherwise, each one in one bench, total classroom, they will move here and there. Okay, whenever the stronger person is coming, immediately sort outing, pairing. So these are the strong ligands. When strong ligands are there, electrons get pairing. So some vacant orbital available. These vacant orbitals utilized by these ligands. But here, when fluorine is there, these are the weak ligands actually. So these, when fluorine is coming, fluorine means suppose one attender is coming in the classroom, there is no change. How they are moving before also, later also, they will move like that only. So they know sort out. Okay, so in that case, the D is utilizing from outside, outer orbital complex. Understood?
Yes, sir.
Okay. So these based on the groups, fluorine, chlorine, bromine is there outside, even water is there outside. NH3, CO, cyanide is there inside. Okay. Whenever outside is using, inside maximum unpaired electrons are present because the electrons are not pairing. Not pairing means 99% chance is there to get more unpaired electrons, isn't it?
Yes, sir.
That's why it is called high spin complexes or spin free complexes. These are high spin complexes or spin free complexes because more spin is there. High spin. Hybridization will be sp3d2. When D is coming from outside, those are high spin complexes. When D is coming inside, D2 sp3, this is the low spin complexes. Got it?
Yes, sir.
Right. Inner orbital low spin, outer orbital high spin. See here, cyanide, nickel cyanide is there. Cyanide is there means obviously electron will get pair up. So magnetic properties we can calculate. Okay, the limitations we can discuss later. Magnetic properties under root of n into n plus 2 mu value. Bohr magnetons. What is n value here? Number of unpaired electrons. Number of unpaired electrons. Okay. Tomorrow we can discuss this. 10 pages remain. 10 means in that 5 or 5-6 pages are there.
Yes, sir.
Oh, good.
Thank you, sir.
Welcome.